Welcome to Learning Outcome 5, our final one, where we meet probability distributions, the patterns that describe how chance behaves. We'll cover three big ones: the uniform, the binomial, and the famous normal distribution. A random variable is just a quantity whose value depends on chance, like the score you get on a die. A probability distribution then lists the possible values and the probability of each one. And whatever the distribution, all those probabilities must add up to 1, because something has to happen. Distributions come in two broad families, discrete and continuous, and telling them apart is where we'll begin. So what's the difference? A discrete variable takes separate, countable values, 0, 1, 2, and so on, like the number of faulty items in a box. A continuous variable can take any value in a range, like height or weight, which you measure rather than count. And a probability distribution is simply the rule or table that gives the probability of each possible value. Counted versus measured, that's the quick test, and we'll come back to it at the end. The simplest distribution is the discrete uniform, where every outcome is equally likely. A fair die is the classic case. Each score from 1 to 6 has probability 1/6. A fair coin is another. Heads and tails each have probability 1/2. Drawn as a bar chart, it looks completely flat. All the bars the same height, which is its signature. It models fair, symmetric situations, a fair spinner, a random lottery digit, anything with no favoritism. Let's work with a fair six-sided die, calling the score x. The probability that x equals any particular x is 1/6 for every x from 1 to 6. Quick check: 6 values, each with probability 1/6, add to 6 times 1/6, which is 1, good. The mean or expected value is 1 plus 2 plus 3 all the way up to 6, divided by 6, that's 21/6, which is 3.5. And the probability that x is 5 or more is the probability of 5 plus the probability of 6, 1/6 plus 1/6, which is 1/3. Every value equally likely, exactly what makes it uniform. Picture that die distribution. 6 bars, each at a height of 1/6. They're all identical, and that flat level profile is the hallmark of a uniform distribution. Add the areas of all 6 bars, and you get a total probability of 1, as always. You'll meet the same flat shape in plenty of fair setups: a die, a spinner with equal sectors, or a randomly chosen single digit. Whenever every outcome is equally likely, this is the picture. The binomial distribution is a big step up in usefulness. It counts the number of successes in a fixed number of trials, and it applies whenever 4 conditions hold. First, a fixed number of trials, n. Second, each trial has just 2 outcomes, success or failure. Third, the probability of success p is the same on every trial. And fourth, the trials are independent of each other. Tossing a coin 10 times and counting the heads is a perfect binomial setup. Here's the formula. The probability of exactly k successes in n trials is c nk times p to the power k times 1 minus p, all to the power n minus k. That c nk is the number of ways of choosing which k of the trials are the successful ones. The p to the k is the probability those chosen k all succeed, and the 1 minus p to the n minus k is the rest all failing. And a handy result to remember: the mean of a binomial distribution is simply n times p. Let's use it. A machine produces items with a 30% fault rate, so p is 0.3, and we check a batch of 10. What's the probability of exactly 2 faulty? Here n is 10, p is 0.3, and k is 2. First, C, 10, 2, the number of ways to pick which 2 are faulty, is 45. So the probability is 45 times 0.3 squared times 0.7 to the power 8. Now 0.3 squared is 0.09 and 0.7 to the 8 is about 0.0576. Multiply it all together. 45 times 0.09 times 0.0576, which comes to about 0.233, so roughly a 23% chance. And the expected number of faulty items is n times p, 10 times 0.3, which is 3. Now picture that binomial. The bars showing the probability of k faulty items for k from 0 to 10, with p at 0.3. The distribution peaks near its mean, n times p, which is 3. It isn't symmetric, and that's because p isn't 0.5. The low end is favored. Very high fault counts are still possible, but they get increasingly unlikely as you move to the right. And as ever, add all the bars together and the total probability is 1. Let's answer at least one question for the same machine. P is 0.3, N is 10. What's the probability of at least one faulty item? The neat root is the complement. 1 minus the probability of none faulty. The probability of none is the probability that x equals 0, which is 0.7 to the power 10, about 0.028. So the probability of at least one is 1 minus 0.028, which is 0.972, about 97%. In other words, it's almost certain a batch of 10 contains at least one faulty item. And notice we've reused the complement rule from outcome 2. Let's set the two discrete distributions side by side. The uniform is flat with equal bars, whereas the binomial peaks near its mean, n times p. The uniform makes all outcomes equally likely. The binomial counts successes across n trials. For the uniform, each probability is 1 over the number of outcomes. For the binomial, it's that c, nk, times p to the k, times 1 minus p to the n minus k. The uniform's mean is just the average of the values, while the binomial's is n times p. A fair die score is your uniform. Faulty items in a batch is your binomial. These aren't just textbook curiosities. In quality control, the number of defective products in a sample follows a binomial distribution. In surveys, the number of people out of n who say yes is binomial too. Uniform models turn up in games, rolling dice, generating random digits, running a fair raffle. The real skill is recognizing which distribution fits a situation, because that's what lets you calculate the risks and the expected counts that decisions depend on. Now the star of continuous distributions, the normal distribution, that famous bell-shaped curve. It's symmetric about the mean, and because of that symmetry, the mean, median, and mode all sit together at the center. Most values cluster close to the mean, while extreme values are rare, tailing off on both sides. The total area under the curve is 1, representing all the probability, and it's pinned down by just two numbers, the mean, which sets the center, and the standard deviation, which sets the width. Let's think about that shape a bit more. The curve is at its highest right at the mean and falls away symmetrically on either side. A larger standard deviation makes it wider and flatter, spreading the probability out. A smaller one makes it taller and narrower, bunching it up. The two tails get ever closer to the axis, but never quite touch it, though the area beyond 3 standard deviations either side is tiny. A great many natural measurements follow this bell shape remarkably closely. The normal distribution comes with a wonderfully handy shortcut. the empirical rule, sometimes called 68, 95, 99.7. About 68% of values lie within one standard deviation of the mean. About 95% lie within two standard deviations, and about 99.7% lie within three. That single rule lets you estimate proportions in your head, without any tables or heavy calculation. Picture those shaded bands on the curve at 68, 95, and 99.7%. Values beyond two standard deviations, only about 5% of the total, count as unusual, and beyond 3, about 0.3%, are very rare indeed. Because the curve is symmetric, each tail beyond two standard deviations holds about 2.5%. Quality control leans on exactly these bands to flag items falling outside acceptable limits. It's the basis of within-tolerance checks on a production line. Let's apply it to real measurements. Adult male heights are roughly normal, with a mean of 175 centimeters and a standard deviation of 7. So about 68% of men fall within one standard deviation of the mean. That's 175 minus 7 up to 175 plus 7, so 168 to 182 centimeters. About 95% fall within two standard deviations, 161 to 189. A height of 189 is two standard deviations above the mean, so only about 2.5% of men are taller. And 196, 3 standard deviations up, is extremely rare, all worked out from just the mean and the standard deviation. Sometimes we want to know precisely how unusual a value is, and that's what a z-score gives us. How many standard deviations a value lies from the mean. The formula is z equals the value minus the mean, divided by the standard deviation. Its real power is letting you compare values from completely different normal distributions on one common scale. A positive z sits above the mean, a negative z below it, and standard normal tables then turn any z-score into an exact probability. Here's a case where z-scores settle an argument. On test A, the mean is 60 with a standard deviation of 10, and you score 75. On test B, the mean is 50 with a standard deviation of 5, and you score 62. Which is better? For test A, z is 75 minus 60 over 10, which is 1.5 standard deviations above the mean. For test B, z is 62 minus 50 over 5, which is 2.4. So even though 75 is the higher raw mark, the z-score shows test B is the stronger performance. A z of 2.4 puts you in roughly the top 1% of candidates. That's the beauty of standardizing. It makes different scales comparable. The normal distribution crops up almost everywhere. Naturally occurring measurements, heights, weights, blood pressure, birth weights, all tend to follow it. So do measurement and manufacturing errors scattered around a target value. Standardized test scores and IQ scores are deliberately designed to be roughly normal. And here's a deep one. Averages of large samples tend to be normal even when the underlying data isn't, which is one of the most important ideas in all of statistics. So how do you pick the right model? Start with one question. Is the quantity counted or measured? If it's counted, with 2 outcomes per trial and a fixed number of trials, that's binomial and discrete. If it's a set of equally likely separate outcomes, that's uniform, also discrete. And if it's measured on a continuous scale, clustering around a mean, that's normal and continuous. Choosing correctly is the key skill, because it decides which formulas and rules you're allowed to use. Count versus measure is your quickest test for discrete versus continuous. Let's bring learning outcome 5 together. A probability distribution lists each possible value with its probability, and those probabilities always sum to 1. The discrete uniform makes every outcome equally likely, a fair die giving each score 1/6. The binomial counts successes in n independent trials, with probability C, n, k times p to the k times 1 minus p to the n minus k, and a mean of n times p. The normal distribution is a continuous symmetric bell curve, where 68, 95, and 99.7% of the data lie within 1, 2, and 3 standard deviations of the mean. And a z-score, the value minus the mean over the standard deviation, standardizes values so results from different distributions can be compared. And that completes both this outcome and the whole Foundations in Statistics unit, from measures of spread all the way to the normal curve. To consolidate the distributions, Crawshaw and Chambers works through the binomial and normal in careful detail, while Rowntree gives an intuitive feel for why the bell curve turns up so often. Corbett Maths and BBC Bitesize both have clear worked examples on the empirical rule and z-scores if you'd like more practice. Try sketching a normal curve for a data set you know, marking on the 68 and 95% bands, and you'll really cement how the mean and standard deviation shape it. Well done for making it through the unit.